Hi, welcome to the Points of Topology Part 2. This is Lifestyle 7, and I'm Shobik, TA of this course, working under reference counseling at Mattress. So, this is the seventh lab session for this course. Before starting the course, please let me know do you have any question or any doubt from previous session? If okay, so and before starting, let me know am I audible properly and is the screen visible to you?
Yes, the screen is visible and you are audible too.
Okay, thank you, Mustafa, for confirming. Now, please let me know if you have any question from previous session, any doubt from previous session. I shall wait for a few
No,
moments. Let me
no,
know
you
your
can
doubts.
continue.
Okay. Okay, thank you, Mustafa. Okay, so in that case, okay, so in that case, let me start with a first problem. So the question is that, so this question tells that, okay, so in between, if you have any doubt or any question, please unmute yourself and ask me, okay? Question. So the question is that if x is metrizable non-discrete space, then x is second countable. So it is true or false. So basically, okay, so basically, what you need to figure out, you need to figure out that first there are two. So first metrizable space means and non-discrete space mean also okay. Now into the second count but not. So basically, you need to find an example, counter example. So in case of metric space, think about it. You will get the answer. Okay, for example, if you consider a real line, so the metrizable space non-discrete, so it is second countable. So possibly it may be true, but think about it or try to prove it that it is maybe false. I mean, you need to find some counter example for that. Okay, try to find out. So basically, you need to try to find some counter example. Try to find counter example. Take your time. Let me know. Seven. So try to find the counter example. So Mustaq, please try to find some counter example for this. So, I mean, the point is the answer is false. I mean, you need to find a counter example. Just take your time and let me know what is the counter example. Okay. Wow. Okay. So the point is that so there is no point of giving huge time for this. So let me. Okay. So the counter example is false. So it is false. Okay. The counter example will be consider disjoint union of uncountably many copies of. So disjoint union of countably many copies of R. Point is that this is metrizable, non-discrete. Of course, it is segmentable, not it is not segmentable. Okay, just why this works. Now you think about it that why this example works. Okay, why this example works. Think. First thing. Second thing is that the question is the space R2 is perfectly normal. It's true or false? The space R2 is perfectly normal. It's true or false? What is a perfectly normal? So what does normal? Normal means if you take any two open set which is disjoint, sorry, if you take any two close disjoint closed set, then you can find an open set containing those two disjoint closed set. Okay, that is what we mean by perfectly normal. Okay, Now try to show that R2 is perfectly normal. Hint is that R2 is a metric space. Think about it. Let me know. Take your time. Hmm. Okay, okay, okay. Got it. So, do you have any guess how to start with? Okay. The point is that the point is that any metric space is perfectly normal. So, why? Think about it. I mean, this is done in the class mode, done in classes. Okay. So the answer is true only. Okay. Now the next question. On Z, we are defining a relation A less than equal to B if A minus B if N. Then this less than is a direction on Z. True or false? True or false? Hmm. So you know the direct direction means if A less than equal to B, B less than equal to C, that means what? A less than equal to C. This is what we mean by direction. Okay. Now show that this gives a direction. Is it true or false? Okay. So think about it and let me know. So yeah, think about it. So basically, what you need to find, so the possible third. So three. I mean, so check the third properties. Check the third property of direction. Okay, check that and let me know. Okay, so the trick is as follows. See, choose some C belongs to Z. Now, point is that so for 2, 3, we cannot find C such that 2 less than equal to C and 3 less than equal to C. Why? Because if this is C, then this does 2 minus C even, and if 3 less than, we get a 3 minus C even, and this implies 1 is even, which is of course not true. So that's why for number 2 and 3, we cannot find any number C such that 2 less than equal to C and 3 less than equal to C. That's why the given this is not find a direction. It's a false statement. Okay. Now go to let X be a topological space and S be a net in X, a subset of X, such that S converges to a point in A, then S is eventually in A. Okay, so it is true or false. Okay, so basically, what is the question? The question is that, so suppose X is topology space is X S be a net in X, and suppose A subset of X says that S converges to a point in A. Then we need to show that S is eventually in A. It is true or false statement. Okay, eventually means after, so maybe eventually means so few terms of S, few terms of S are not in A, but apart from finitely many terms of S, all the terms of S are in capital. This is what I mean by we mean by eventual in A. Okay, so Okay, so now try to figure this out the problem by yourself. Take your time, let me know. In the meantime, let me find some other questions. Hmm. Hmm. Okay. So, so the solution show it is false. Okay. How? The point is, like A to be any subset of the which is not open, then we have proved that there exists a net yes converging to a point in A but not eventual in A. Any subset which is not open, then we have proved that there exists a net S converging to a point in A but not eventually in A. Okay. So yeah. So the specific example you can take x equal to double down 01 and tau be the Sierpinsk Spersky topology. Okay, Spersky topology that is phi 0 holes at x. Okay, Now take the constant sequence Sn is equal to 0. Okay. Then A is equal to, so then this implies A is equal to A. So this tells that that S converges to 1, but S is not eventually in A. So that is the argument. Okay. Wow. So that is the thing. But S is not eventually in A. So yeah, so that is the contradiction. So hmm. So basically, a subset, any which is not open, then we have proved that there exists net is converging to a point A, but not eventually A. X single double tone 0 1 we are taking, and then because it's Sparks topology, then finally you are getting that Sn, if you take the sequence Sn to be 0, A is equal to 1. This still the S converges to 1, but S is not eventually, that's what is false. Okay. Is the argument clear? Okay. So now the next question is that the intersection of two eventual subsets is eventual. True or false? Think about it. Just you need to explore the definitions. There is nothing to do extra. Okay. Intersection to eventual subset is eventual. Think about it. Let me know. Oh. So, so point is that it is false. It is true. Okay. Why? Because E and F. So E and F be to eventual subset of a directed set D. Then there exists A B belongs to D such that what is this triangle? How it is coming? Such that whenever A less than equal to X, X less than equal to E, and whenever B less than equal to X, X less than equal to F, let C belongs to D such that A less than equal to C, B less than equal to D, since D is directed. Now X less than belongs to D such that C less than equal to X. So this tells that A less than equal to X, which implies that X belongs to E. Again, X less than equal to F. Hence, X belongs to E intersection F. So let me explain. Hmm. E and F are to eventually subset direct set during. So now there is A B belongs to D such that whenever A less than equal to X, then E and B less than equal to X less than F. Suppose we are taking C belongs to D, A less than equal to C, B less than equal to C. This is not D is directed. Now X belongs to D such that C less than equal to X. This implies A less than equal to X, which implies X belongs to E. Again, X belongs to this tells X belongs to intersection F. Okay, that is the point. Okay, is it clear? Please let me know. Okay, so take your time. Please let me know. So okay, so okay, so now I hope this argument is clear. Now let's go to subjective part. First question is, give an example of a topospace X and a family C of closed sets of X such that there exists such that the reverse inclusion is not a direction. See, give an example of topological of X and a family C of closed sets of X as there such that the reverse inclusion is not a direction in C. So try to solve by yourself. Take your time. Let me know. In the meantime, let me find some other questions. Okay. So you need to find a space X and a family close of C says that the reverse inclusion is not a direction of C. Okay. So please think about it and let me know. Okay. Okay. This question seems not run. Okay. Hmm. Hmm. So, so this question not possible to do, I guess. Okay. Anyway, so so I'm going to give you the example. You should figure it by yourself why this shall not work. Okay. Okay. Before that, let me know whether it will work fine. Okay. Okay. So take x to be r and c to be 0, 1, 0, 2, 1, 3. Okay. X to be r, c to be 0, 1, 0 to 1, 3. Okay. So check this example shall do the job. Okay. Take your time, you should figure it out. Okay. It is an HW. Now next question. Next question is give example of an infinite topo space X which is not an indiscrete space and the net S such that yes converges to every point of X. Give example of infinite topological space X which is not an indiscrete space and a net S such that S converges to every point of X. Okay, so take your time, think about it. Let me know. So you need to find an infinite space in which not an indiscrete space and S converges to basically you need to find some space where any sequence converges to any point. So try to figure out example like that. Okay, take your time. Please let me know. Hmm. Okay. Okay. So, so, one minute. So the example goes as follows. Take x equal to n with cofinite topology. X equal identity in n to n. Why? Because the point is, if we take any x n belongs to n and take an open set, then u minus singleton n, this is open in n, right? That means, but we are in cofinite over. That means this is a finite set. That is, U contains infinitely many elements of, yes. Hence we are done. Okay. So basically it's the same argument. It is a same argument as in the fact that the sequence 1 to the power n converges to any point in cofinite topology. The PST part 1, it was done. Okay, so they're the same thing. So there is nothing new in reality. Okay. Hmm. Okay, okay, that's fine. Okay, so now the next question. The next question is that give an example of uh, a co-final subset of a directed set which is not. Give an example of a co-final subset directed set which is not eventual. Okay, so hmm. So okay, so try to find out sorry, try to find out some example for that. Take your time, let me know. Mm. Oh, so the example is the following. Hold on, please. So the okay. So the example is following, namely, take d is equal to r with sorry, take d is equal to r with usual order and let d prime is equal to z. Take d is equal to with usual order, d prime is equal to z. Okay. So that is the thing. Okay. So now I think there is no need to explain why this is working. There is no point to explain it, I guess. Okay. Now the next question. Next question is give an infinite topo space X and a net S from D to X such that every point of X is a cluster point of S but none of them is a limit point of S. Given infinite topological space X and the net yes T2X shows that every point of X is a cluster point of X, but none of them is a limit point of X. Okay. So yeah. So give an answer for this. So try to provide an example for this. Okay. Take your time, please let me know. So try to find out an example for this. Okay. That is the thing. It should not be hard. So you can start with cofinite topology. Okay. So yeah, the cofinite topology should work. Think about it and let me know the answer. Mustaq, please take your time. Hmm. So okay. Hmm. So the answer goes as follows. Take X to be n under cofinite topology and yes is equal to 2x be the sequence 1 1 2 1 2 3 1 2 3 for dot. Okay, but of course none of them is midpoint, but clearly none of them limit point of S. Okay. So yeah, so that is the argument. X equal to n and cofactor topology. S into X be a sequence. So we are taking this sequence and but none of them will be point of S. Okay. So it is clear. Take your time. Let me know whether are you able to figure this out or not. But it's not that much difficult. Okay. So yeah. So take your time. Let me know. Hmm. Okay. So yeah. So the next question is the following. Next question is find the sequence S into X where X is any set and a subset and subnet T which is not uh, subsequence of X. Find the sequence Yas from N to X where X is any set and a subset T which is not a subsequence of Yas. Hmm. So yeah, so that is the point thing. So take your time, let me know. So basically, so try to. So hint is try to replicate the previous example. Try to replicate the previous example. Okay, take your time, let me know. Okay. So, hmm, so, so the answer is that take x equal to r. Okay. Take x equal to r, s equal to id, t to be 1, 1, 2, 2, 3, 3, 4, 4, dot, dot, dot. Then clearly T is a subnet since we can define P1 is equal to P2 is equal to 1, P3 is equal to P4 is equal to 2, P5 is equal to P6 is equal to 3, and dot dot dot. So this is one example. Alternatively, yeah, so there is nothing. So yeah, so that's also yeah. So basically we are choosing x to be the whole real line, x s equal to identity TTV 1, 1, 2, 2, 3, 3, 4. Clearly it is a subnet, but of course not a subsequence. So that is the argument. Okay. Is that clear? Please let me know. So out of the six questions, please let me know is everything clear or not. Okay. So I hope this assignment is clear to everybody. So now let's move for the next assignment. Okay. So let me go for assignment 7, I guess. Hmm. So So, okay, so it seems that there is assignment 7, but that assignment 7, still there's time left on submission. So, let's not get into assignment 7. So, I shall now give you some extra problems. Okay, so, hmm, okay, so let me find some good one. Hmm. Hmm. So, okay, so, mm, see there is any previous assignment left or not. Let me figure this out. Okay. So yeah, so I somehow missed assignment one. Okay. So let's start the assignment one. Of course, first let's MCQ. Okay. So so the question is true false question. True or false question. Okay. Let V be a normed space and given T belongs to BV, there exists an operator EXPT in BV such that EXPT is summation 0 to infinity to the power n by factorial n. Okay. Suppose V is a normal space. T be a bounded linear operator on V. Show that question is there is an operator EXPT in B which says that EXPT is equal to T to the new. Is such a thing true or false? Okay. So okay. So think about it. Hint is that It is not a Banach space. See, but if it is Banach space, then this is true. All we all know. But here, this thing is not a Banach space. Okay. So it is only known space. So possibly one can guess such a thing is not going to be true. So you need to find a common example. So the exponentiality cannot be equal to t factorial. And that means what? You need to find t on some suitable space as a summation t to the power n by factorial n. This thing is not making sense. That is, this summation evaluated at some particular point is not making sense for you. Okay, something like that you have to show. Okay, take your time, think about it. Let me know. Okay, so take your time, think about it. And let me know the answer. So you need to find some example which is not Banach space. Okay. Okay. So so point is that, so choose phi to be, or to the power omega, that is, we'll consider all the sequence elements such that x equal to 0 except finitely many cases. Let t be the shift operator. We're choosing the operator t with shift, that is t of en is en plus. Then the summation 0 to t to the power n e1 by factorial m. This thing does not make sense inside phi. T with a shift operator. T of En is equal to En plus 1. The point is t to the power t to the power n e1 factor. This thing does not make sense inside phi. So that is the argument. Okay. V is equal to the omega t shift operator t to En is equal to n plus 1. So t to the power n e1 by in fact this does not make sense inside phi. Okay. So that is the argument. So yeah, so it has so this is so it has nothing to explain indeed, I guess. So now let's go to the next problem. So basically it's a false. So it's a false statement, okay? It's a false. Now go to the next question. So it is a true or false question. The question is that let V be a Banach space and given Tx belongs to BV, we we have exponential of t plus s is equal to exponential t compose exponential of s. Or exponential t summation 0 to infinity t to the power n by factorial n. Okay, so such a thing is true or false. I mean, so basically, as same as the previous problem, this problem also try to figure out some counter example. Okay, in general, such a thing, of course, not true. I mean, so try to figure out. Take your time. Let me know. Uh, okay. Hmm. Okay. 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 So now, okay, of course, such a thing is not true. So solution is as follows. So false. First of all, it is false. Choose V to be R2. Then of course, BV is equal to M2R. Okay. Consider T equal to 1, 0, 0, 0. A is equal to 0, 1, 0, 0. Then EXPT that is equal to EXP1001 and EXPS that is um, 1101. Okay, then we have T plus A is equal to 1100. So if we calculate, then this takes, sorry, what happened? EXP of T plus A, that is coming to be EXP1, EXP1 minus 1, 0, 1. Okay, and that's clearly EXPT plus S not equal to EXPT, EXPS. And indeed, the claim holds if T and S commutes. In general, this such a claim doesn't hold. So the point is that EXPT comma S such a statement is always false. Okay. So here it construct one example of T and S, and has shown that that given condition is not getting satisfied again. So there is nothing more to explain. Okay, true or false. Okay, let V be a Banach case. Sorry, let V be a Banach space, and given T belongs to BV, EXPT is an invertible operator. Solution. We can prove that. We can prove that if Ts is equal to xst, then exponential of x plus t is equal to x. Sorry, why am I writing the solution? Please take your time, think about it, and let me know. Here belongs given t belongs to b. We need exponential of t is an invertible operator. Okay. So yeah, so try to construct such example. Take your time. Please let me know. That is, you need to find some operator t prime, so the exponential of t composite t prime is identity. Okay, take your time. Let me know. Okay. Okay, solution. The point is that we know that if S here commutes, that is St equal to Ts, then first of all the answer is true. Okay, so Ts, then exponential of t plus s, that is exponential of t compose exponential of f. Okay, now exponential of t compose exponential of minus t, that is exponential of 0, that is identity. So this tells that exponential of t, its inverse is equal to exponential of minus t. That is the argument. Okay, that's what is true. So there is nothing to explain more, I guess. Let V be a normal space and T belongs to BV. Define F BV to BV by f of t is equal to t square. Okay, then which of the following is correct? Okay, so the options are: f is not differentiable at 0. Option B, f is differentiable with f is differentiable with the f the linear map to D. C is f is differentiable with the f t h t h plus ht. Df is continuous. Okay, so this is the fourth statement. Now question, which one of them is true? So T is a linear bounded linear operator on a given nominal space, and the map is T going to T square. Okay. Now question, if is differentiable or not differentiable, there's four options. So try to figure out by yourself which one will be true. Okay. Take your time, let me know. Just you need to exploit the definitions, and yeah, that's what you need to do. Please let me know. Take your time. Hmm. Hmm. Okay. So, so now the point is that we shall prove that df th that it should be equal to th plus ht. For that, first note that h going to th plus ht. This is a continuous map. Okay, this is a continuous linear map. Then limit h going to 0 t plus ah whole square minus t whole square ph plus ht divided by norm of h that is equal to limit h going to 0 h square by norm of h. That is of course equal to, so there's nothing to explain, I guess, right? And this automatically tells the option A, option B is false. So there is nothing to explain more, I guess. Okay. Yeah. So is that okay? Basically, we check this limiting value is going to zero or not. This is the main crucial step. Okay. That is the thing. So yeah. So yeah, that's one thing. Now, the next question. There exists a norm on the space of polynomials in R. That is, P is equal to summation ai xi. ai belongs to R, n belongs to n. Such that P is a Banach space. Hmm. So yeah. So that's, I mean, so point is that, I mean, so I'm, so for sake of simplicity, I'm telling the answer is false. So you need to show that you cannot define a norm on such a space. Okay. Now try to prove it that such a thing statement is not true. Okay. Take your time, let me know. Okay. Okay. So the point is, we can write P is equal to union of Pn. So basically, Pn means up to dimension n polynomials, up to n degree polynomials. Okay, and each Pn is complete with this norm. Okay, now Pn proper closed subset and Pn nowhere density P. So this implies that the P is a countable union of closed and nowhere dense subsets under any norm, and hence our first category space. Okay, now by pair category theorem, it cannot be a complete matrix. Okay, so yeah, Hmm. So basically, if suppose suppose such a norm exists, okay, then the problem will be what? If such a norm exists, then we are considering P is equal to mu of Pn. Pn without any polymers, okay. If Pn is complete and Pn with closed subset, Pn is no higher proper density. So this tells that Pn will be PL will be countable in closed no dense subset and anyway hence a first category space. By bare category theorem, it cannot be complete metric space. So that is the argument, okay? So there is nothing to explain.